Good morning, students. Now we discuss the character group. So as we have proved earlier, that if G is a finite abelian group of order n, then there exist exactly n distinct characters for the group G. So we will denote the principal character by F1, and the other characters will be denoted by F2, F3 up to Fn. So basically, we will denote the n characters of a finite abelian group of order n by f1, f2, fn, with f1 to be the principal character. So now we prove, now we define an operation, and we will prove that the collection of all the characters that forms an abelian group of order n. So we have this theorem. So if we define multiplication of characters, this is theorem 6.9, if multiplication of characters is defined by fi fj, which is again a character defined by fia and fja, means just pointwise product of the functions for each a in G. Then the collection of all the characters of G. Again, this forms an abelian group of order n. And we will denote this group by G cap. Identity element of this group will be the principal character f1, and inverse of f1 is the reciprocal 1 upon f1. So we can verify all the postulates to being a group. Because we have defined the multiplication as pointwise product, so we can easily prove that for any two characters fi and fg, the product fi fj, that is also a character. Because to be a character, we need only two properties. One is multiplicative property and other is non-vanishing property. Similarly, we can prove associativity, because pointwise product is always associative. The identity element is the principal character f1, and inverse is 1 upon f1. Now we have this thing for each character f. We know mod of fa is 1, because we have proved earlier that fa is a root of unity. So mod of fa is 1. This means reciprocal 1 upon fa, this is equal to conjugate of fa, because mod of fa is 1 means fa into fa conjugate, this is 1. So 1 upon fa is conjugate of fa. So that's why we can define another function f bar by, of course this f bar is a complex valued function defined on the group G. So we can define f bar by f bar at a is conjugate of fa. This is also a character of G. Further, this character f bar a, that is actually 1 upon f a, and this is f of a inverse, because we know f of a raised to k is equal to f a raised to k because of the multiplicativity of the character. So 1 upon f a is f of a inverse for every a in G. So for each character f, we can define another character f bar, which is given by f bar at a is f of a inverse. Now we prove some orthogonality relations for characters. So for this section, we will assume that G is a finite abelian group of order n with elements a1, a2, a3 up to an, with a1 to be the identity element, and we will assume that f1, f2, fn, these are characters of G, with f1 be the principal character. And so we have a notation. We will denote by A, which is actually A of G, where G is this given group. B, n by n matrix Aij, whose element Aij is defined by Fi at Aj. Because we are assuming A1, A2, An are elements of G, and F1, F2, Fn are characters. So Fi at Aj will be denoted by Aij, and we will make a matrix A by these elements Aij. So now we'll prove that this matrix A has inverse, and then we will use this fact to deduce the orthogonality relations for characters. So firstly, we determine the sum of entries in each row of A. So we have theorem 6.10, which says the sum of entries in the row, in the ith row of A, is given by sum of entry in the ith row is given by summation f I a r, r varying from 1 to n. This denotes sum of all the elements in ith row. So this will be equal to n if fi is principal character, which means if I is 1, because we have assumed f1 is principal character. So that is I is equal to 1, and otherwise it is 0. So this theorem basically says that sum of all the entries in the first row, which is corresponding to the principal character, that is n, and all other rows, their sum is 0. Let us prove it. Let us define S as sum of elements in ith row. Now if fi is equal to f1, that is I is equal to 1. If I is equal to 1, then because we know principal character is 1 at every element, then each entry fi ar, this is 1 for all r varying from 1 to n. So sum will be obviously n. This means S is n. Now if I is not 1, that means the character is not principal character. Now since this is not principal character, so there exists an element B in the group G for which FIB is not 1. Now we know A runs through the elements of G. So if A runs through elements of G, then BA also runs through elements of G. So we can write here, since AR runs through elements of G, therefore BAR runs through elements of G. So it means S is S can be written as FIBAR. If AR is element of G and we have chosen element B again in G such that FIB is not equal to 1, so FIBAR. BAR, they are also all the elements of G. So we can write S like this. Sorry, R is equal to 1 to N. So because of the multiplicative property, this can be written as FIB, FIAR, R varying from 1 to N, and FIB can be taken outside because it is independent of R. So summation FIAR. So this is FIB into S. So we have proved S is equal to FIB into S. But FIB is not equal to 1. So it means S is 0. This thing is possible only when S is 0 because this is not 1. So we have proved the sum when I is equal to 1 the sum is n, and when I is not equal to 1 S is 0. So now we will use this theorem to prove that A has inverse. A is invertible matrix. Now let A star denote the conjugate transpose of the matrix A. Conjugate transpose means taking the transpose and then conjugate of all the elements of A. We get a new matrix which is called the conjugate transpose of the given matrix A. So let A star be conjugate transpose of A. Then we have this thing, A into A star is n into I, where I is n by n identity matrix. So from this relation we can say A is invertible matrix, which means n inverse into A star. This is inverse of the matrix A. So this is invertible matrix. So let us prove. Let B is A into A star. So we have to prove B is n into I. So if B is A into A star, and of course we will suppose that B is the matrix represented by the elements Bij, where this Bij is given by summation FIAR Fj bar AR. R varying from 1 to n. So why we have written Bij like this? Because B is A into A star. So Bij will be I rth element of A and then rjth element of A star and then sum of those type of elements varying from R varying from 1 to n. So I rth element of A is FIAR and rjth element of A star is basically j rth element, conjugate of j rth element of A. So conjugate of j rth element of A is Fj bar AR. So this is summation R varying from 1 to n, because we have defined the product of characters by pointwise product. So we can write like this. So this is summation. Now we know this Fi into Fj bar, this is again a character because product of two characters, that is also a character. So we can write them as FKAR because this product is again a character. Where what is this Fk?